Hi statisticians. Today our lesson is on experimental design. Let's get started. Some of the most in-demand research positions and jobs are in STEM or science, technology, engineering, and mathematics. Research positions and jobs in these areas tend to come with higher salaries and can be pretty rewarding. However, for a long time, there's been a persistent gender gap in STEM research and in STEM careers. Now, before we explore those gaps, let me name something right off the bat. When analyzing gender gaps in STEM, most of the data collected in the field tends to only capture folks who identify along the gender binary, male or female. There needs to be more data collected on people working in STEM who don't identify by this binary. So even though I'm talking about gaps along the binary lines, there is a more insidious gap here in that we don't have good data that describes truly people who research or work in STEM fields. And we need more precise data collection in the future to address that issue. However, even if the data that we have does not fully capture everyone, it's still worthwhile to analyze trends among what we can already see based on the data that we already have. And it's pretty clear that males have traditionally been overrepresented in STEM research, with nearly 65% of all science paper authors in 2005 being male and only 35% being female. And that gap becomes even more extreme as we look at specific STEM subfields, such as engineering, physics, and math. Even more recently, as of 2020, workplace surveys have shown a stark gender gap exists in the relatively newer field of data science. You, as an amazing student in the field of statistics, should feel concerned and see that this merits investigation for potential causes. And that brings us to today's key question. What causes gender gaps in STEM fields? With this question in mind, we'll move on to our notes. We're going to cover 3 topics today, starting with extraneous variables and confounding. So, we're wondering why there are gender gaps in science, tech, engineering, and math research. One theory could be that there is hiring discrimination in STEM research labs. If that's the case, if we were to investigate a bunch of STEM research labs, we might find that many of the labs discriminate in their hiring practices, and that this discrimination causes the gender gaps we see in STEM research. But this is just one possible explanation. It could also be that there are just fewer women applying to STEM research jobs, so the gaps can still occur even without any direct discrimination in hiring. Or it could be that labs receive more qualified male applicants, resulting in the final gap in who is hired. Or it could be that female applicants disproportionately apply to more teaching-focused labs, who tend to publish less research, hence the gap we see in paper authors down the road. Or it could be that female applicants disproportionately apply to Tier 1 university labs who may be more selective. Thus, they may get hired less often because they are only applying to a more selective pool of institutions who will hire fewer people. As we can see, there are in fact many possible causes of the gender gaps we have seen. So, to recap, our initial theory is that hiring discrimination may cause gender gaps in STEM. So, hiring discrimination is our explanatory variable, and it's explaining trends we are seeing in the response variable, gender gaps in STEM. But there are other variables that could also influence these gender gaps. We call these variables extraneous variables. And when extraneous variables like these are associated with both the explanatory variable and the response variable, they are called confounding variables. In other words, they confound the relationship between our explanatory and response variables, making it unclear if they actually have a true causal connection, or if they just coincide with other factors at play. Hence, when confounding is present, we can't draw causal conclusions. With these other confounding factors at play, we can't say for certain whether hiring discrimination is the true ultimate cause. So, how can we get around that? Thankfully, we have a way, and it involves designing good experiments. A group of Yale researchers conducted a now famous Jen-John experiment to try to directly test for hiring discrimination. They made fake application materials that were completely identical except for one aspect, the name. They made some application materials for a fake applicant named John and other application materials that were completely identical except for the name was Jennifer. So everything was the same, the information on the resumes, the personal statements, and all other materials exactly the same except for the names. The study included 127 science faculty from labs all over the country. The researchers then took their fake job application materials and randomly assigned the lab faculty to either receive a John application or a Jennifer application. In total, 63 lab faculty were randomly assigned to evaluate the John application materials, and 64 were assigned to receive the Jennifer application materials. After evaluating the application materials, the faculty then rated the applicants for their competence, hireability, and they also gave them an estimated starting salary. These evaluations were then compared across the two groups. Before diving into the results, let's look at the components of this experiment. The science faculty members are what we call the experimental units, or the subjects in the study that were randomly assigned to the treatments. The explanatory variable, the thing that we believe will cause the difference, and the only variable that has changed between the treatment groups, is the gender of the name on the application. The treatments applied here are the names Jennifer and John on the application materials. And finally, the measured response variables are the ratings that the faculty gave to the applicants. To make sure that we have a good causal inference for this study, we can make sure that it satisfies the 4 principles of experimental design. First, comparison. The study must compare at least 2 treatment groups. In this case, the study is comparing applicant evaluations across the Jennifer group and the Jennifer group. So this is accomplished in this design. Next, there has to be a random assignment to treatments. This might be the most important principle, and here's why. Among the 127 faculty, extraneous variables still potentially exist, such as the ones we mentioned earlier. Some of the labs may be teaching focused, other may be more selective tier 1 universities. By randomly assigning each lab faculty member to one of the treatments, we get groups and a distribution of those extraneous factors that might look like this. When putting them all together, we see that the random assignment balanced the extraneous variables between the groups, helping to ensure that both groups got about an even amount of faculty from labs that were more teaching focused or were more selective. That means that these variables no longer confound the relationship between gender and hiring, since they are now included evenly in both groups. As we saw in the Jen-John study, they did in fact randomly assign the faculty members to either receive John or Jennifer application materials. So the potential for confounding is reduced and the random assignment principle is satisfied. Now, it bears repeating, random assignment is the most important principle of experimental design, and that's because it is key to lock in causal inference by allowing us to see causal trends without confounding in the way. And one quick note, when we talked about sampling in an earlier lesson, we saw that random sampling reduces bias. And now in experiments, we say that random assignment reduces confounding. These concepts are analogous, and it's important to get the vocab right in the different scenarios. The next principle of experimental design that comes into play is replication. And that is that there should be many experimental units in each treatment group. So let's imagine that we only had 2 faculty members in each of the different labs. And let's just imagine that both of these faculty members really like to have coffee in the morning. But at one of these labs, the coffee machine is broken, and that reviewer ends up being in a terrible mood that day. So imagine that we randomly assign the Jen and the John application materials to these 2 faculty members and have them rate the application materials. Our application may look like this. And as we might expect, the Jennifer applicant gets a terrible rating. However, it might not be that professor had always given Jennifer a bad rating. It might just be that they had been in a bad mood that day. So that rating might not be due to discrimination. It might be due to their bad mood. So by getting more participants in each group, a lot more participants in each group, the effect of the broken coffee pot is minimized. And that's why it's important to have replication. Including many in each treatment group reduces the impact of a chance variation in the extraneous variable between the groups, and it makes any treatment effect easier to detect. So with 63 and 64 people in each group, there was adequate replication in the John-Jen study. And finally, that brings us to the design of the experiment should have direct control over extraneous variables as necessary. In the Jen and John experiment, the applications were completely identical of all extraneous variables except for the name of the applicant, one being a male and one being a female name at the top of the resume. This eliminated the possibility of labs receiving fewer female applications or the male applicants being more qualified. Since all of the science faculty members were looking at the same qualifications and almost exactly half were looking at one gender and almost exactly half were looking at the other, that means that we further utilize direct control to ensure controlling for certain important extraneous variables. Therefore, the Jen and John experiment accounts for all of the components of experimental design. And since it was well designed, causal conclusions are possible. So let's finally get into the results of the study. It turns out that the applications with the John name were given a mean competence rating of 4.1, a mean hireability rating of 3.8, and an average starting salary estimate of $30,238. For the application materials labeled Jennifer, which were completely identical to the John application materials, other than the name, they were given a mean competence rating of 3.3, a hireability rating of 2.9, and an average starting salary estimate of $26,508. In all 3 measures, Jennifer scored lower than John with exactly the same application. And because this study satisfied all principles of experimental design, we can say that there is evidence that the name caused the differences. Now, it's also worth noting that these differences were also found to be statistically significant. That is, that the differences are so large but they're unlikely to have happened by chance alone. We'll study that idea of statistical significance in more depth later in the course, but for now, just know that these differences are so large that they're unlikely due to chance. And now, we'll move on to our last topic, which is describing an experiment. How would we describe this experiment to others? So first, we'll take a look at our specific study. To begin with, we need to describe the randomization process for the experiment. How each experimental unit is assigned a number, the numbers are put on slips of paper, thrown into a hat. After mixing well, we draw out the slips without replacement and assign random groups. Once we have that random assignment, we can compare the responses between the groups to see what happened. Let's see how this works with our Jen and John experiment. With 127 faculty numbers, we number them 1 to 127. We put the assigned numbers on identical slips of paper, put them all into something like a hat or a bowl, and mix them up. Since we have an odd number total, we can't have exactly the same in each treatment. That would be ideal. So instead, we're going to draw 63 slips without replacement, and those first 63 are going to be assigned to the first treatment. We also could have picked 64 for the first treatment. That is interchangeable. Once we have that assignment, record and compare the compliance ratings, the hireability ratings, and the starting salary estimates between the two groups. Now that brings us to our discussion for the day. The John and Jen experiment showed that the name caused these differences in how the applicants were evaluated. Considering the gender gaps that exist in STEM, our question is, does the Jen and John study prove that hiring discrimination is the only cause of gender gaps in STEM? Or might there be other causes as well? Take a moment to jot down your initial thoughts to these questions, and we'll discuss them in class. That's it for today, statisticians. We'll see you next time.